Hello friends, welcome back to the online lecture series of fluid mechanics, and we were discussing the various fluid properties, and the latest property which we were discussing was the surface tension. In the previous chapter we were discussing the various consequences of surface tension, or rather how the surface tension helps to keep the system in equilibrium. In that, first of all, we have seen the energy minimization principle. So the effects of surface tension started with the energy minimization principle. I already cited few examples such as why a liquid droplets are always spherical in shape, and that is because of the energy minimization principle attributed to surface tension. Now, reviewing liquid droplets, in order to come in equilibrium, they tries to minimize their surface energy, and for reducing the surface energy within the constraint of a fixed volume, the only way they can do so was to reduce their surface area. And for a fixed volume, we know that a sphere has the least surface area. So in order to reduce its surface energy or to minimize its surface energy, a liquid will try to reduce the surface area, and so it takes the form of a sphere. Moving forward, we have the second consequence of surface tension. Now, the second consequence of surface tension is that it is due to surface tension that a curved liquid interface in equilibrium results in greater pressure at the concave side of the surface than at its convex side. Let me write it that it is due to surface tension that a curved liquid interface, a curved liquid interface in equilibrium will have a greater pressure, at its concave side, greater pressure at the concave side of the surface than that at its convex side, at its convex side. So because of surface tension, we have, suppose, let us say that this is any curved interface, liquid interface. Now for this, we have this side will be the concave side and this will be the convex side. Now it is due to surface tension that the pressure that will be acting at the concave side will always be greater than the pressure that will be acting at the convex side. So let us say that the pressure acting at the concave side, let us say that this is Pi, and the pressure acting at the convex side, let us say that this is PO. So this is your convex side and this is the concave side. Now, according to our statement, we have the pressure at the concave side will always be greater than the pressure at the convex side, or we will have Pi always greater than PO. Or in other terms, we can also say that there will be a net pressure that will be acting on the curved liquid interface, a difference of pressure of say del P that will be acting on the curved interface, and it will be directed like this. Here del P will be equal to Pi minus P naught, as we have the pressure at the concave side greater than the pressure at the at the convex side or the outside. Now, to understand this, we have a very important equation which we call the Young Laplace equation. For that, we need to deduce some expression. So let us consider an elemental liquid surface separating the bulk of liquid at its concave side and a gaseous substance or any other immiscible liquid at the convex side. So let us say that we are considering an elemental surface of the interface. So it is curved on both the sides. Now this is the curved interface which we are considering, and here we will consider that both of these sides will be having they will be subtending an angle, say d theta 1 and d theta 2 with the center of curvature, and they have a radius of curvature of r1 and r2. So let us say that this side is extending an angle of d theta 1, and the other side is also extending an angle of, say, d theta 2. Also here we will consider that the radius of curvature of this side is r1, and for this side let us say that this is r2. Consequently, the length of the elemental surface may be calculated as, for this side, for this length, we will have, what will be the length? It will be r1 into d theta 1. So this length is r1 d theta 1, and this length will be r2 d theta 2. Now we suppose the coefficient of surface tension for the considered liquid, let us say that it is sigma. So the force due to surface tension will be acting on both the sides along the length. So let us say what will be the force that will be acting in this direction. We know that sigma is equal to the surface tension force upon the length of the interface. So the force due to surface tension will be calculated as sigma into the length of the interface. So the length of the interface, in this case, we will take the surface tension that will be acting overall on this length. This length is r2 d theta 2. So the surface tension force that will be acting here will be sigma r2 d theta 2. Similarly, along this side also, sigma r2 d theta 2. Now for this, we again have surface tension that will be acting along the entire length, and we may denote it like this. For this we will have sigma, the length is r1 d theta 1, so it will be sigma r1 d theta 1, and here also we will have sigma r1 d theta 1. Now let the surface be subjected to a uniform pressure, say Pi at the concave side and P naught at the convex side, acting perpendicular to the elemental surface. Now, since they are acting perpendicular, we would like to resolve the force due to surface tension in the perpendicular direction. So, through geometry, we can do that. Let us consider one by one both the sides. So, this will be our first side, which is r1 d theta 1, and we may draw this one like this. This will be d theta 1. Now, the force due to surface tension, let me draw it by using dotted lines and making it more curved. Now we have the surface tension force that is acting along this elemental surface as sigma r2 d theta 2, For this we have sigma r1 d theta 1. So since we are considering the first diagram, so here we will have forces like this. So here we have sigma r2 d theta 2 and sigma r2 d theta 2. Now since we are interested in resolving the forces along the perpendicular direction, let us do one construction. We would like to extend the lines. Not because to resolve this force into its perpendicular direction, we need the angles, these angles. So how can we calculate these angles? Let us say that, let us denote the angles, this angle as x. Let us say that this angle is y. This angle, let it be z. Let us say that this is w. We may now write this as a and b. Now taking this triangle, we have z, angle z plus x. This will be equal to 90 degree. So we have angle z plus angle x is equal to 90 degree. Angle y plus angle w will again be equal to 90 degree. So we have angle y plus angle w is equal to 90 degree. Now let us add this. We have angle z plus angle w plus angle x plus angle y. This will be equal to 180 degree. And we know we have already denoted this angle, the sum of angle x and y. We will say this d theta 1. So we can say that angle z plus angle w plus d theta 1 is equal to 180 degree. Now also we have this angle. How to calculate the angle A? We have angle A plus Z. This is equal to 90 degree. So angle A plus Z is equal to 90 degree. Now here in this triangle we have these both sides are radius R1 and R1. So this overall this triangle becomes an isosceles triangle, making the angle Z and W equal. So instead of Z plus W, we can now write down twice of angle Z plus d theta 1 is equal to 180 degree, or simply 2 twice of angle Z will be equal to 180 degree minus d theta 1, or angle Z can be written as 90 degree minus d theta 1 upon 2. Also we have angle A plus angle Z is equal to 90 degree. So we have angle A plus angle Z is equal to 90 degree. So angle A will be equal to 90 minus angle Z, and for angle Z we have 90 degree minus d theta 1 by 2, which gives us 90 minus 90 will be cancelled out, and what will be remaining? D theta 1 upon 2. So we have angle A is equal to d theta 1 by 2. So for this angle becomes, A becomes d theta 1 by 2, and similarly B will also be d theta 1 by 2. Now since this angle is d theta 1 by 2, and now we can resolve. So we have condition like this: for any given force, if we know this angle as theta, so this component of the force will be F sine theta, and this will be F cos theta. Now similarly in this case, the force is sigma R2 d theta 2. So we will have a downward force that will be acting because of this force sigma R2 d theta 2, and that will be equal to sigma R2 d theta 2 sine of d theta 1 upon 2. Similarly, for this force also we will have the same sigma R2 d theta 2 sine of d theta 1 by 2. So overall, the force in the perpendicular direction can be written as sigma R2 d theta 2 sine d theta 1 by 2 plus sigma R2 d theta 2 sine d theta 1 by 2, which gives us 2 sigma R2 d theta 2 sine d theta 1 by 2. We can do the same for this side also, and we will get similar results. And so we will have a total force due to surface tension will be 2 sigma R2 d theta 2 sine d theta 1 by 2 plus 2 sigma R1 d theta 1 sine of d theta 2 upon 2. Now this, let us try to bring this elemental surface in equilibrium, and we know that the pressure that are acting on the concave side and the convex side, it is Pi minus, it is Pi and P naught, and we have a differential pressure of Pi minus P naught. So we know that for intensity of pressure is given as force upon area. So the force due to pressure Fp will be equal to the intensity of pressure into area. Here the intensity of pressure is del P or Pi minus P naught, and the area can be calculated as R1 d theta 1 into R2 d theta 2. So this must be equal to, since the net pressure is acting along the positive x-axis and this is acting along the negative x-axis, so we can now equate this. So we will have Pi minus P naught into the area of the elemental surface, which is equal to R1 R2 d theta 1 to d theta 2. So this is the force balance. Now we know that here the angles are very small, and so for very small angles we can take the sine of d theta 1 upon 2 for very small angle. For a small angle, we can say that sine of d theta 1 upon 2 is approximately equal to d theta 1 upon 2, and similarly for sine of d theta 2 upon 2 can be written as simply d theta 2 upon 2. So replacing the values of sine d theta 1 by 2 as d theta 1 by 2 and sine of d theta 2 by d theta 2 by 2, we have twice sigma r2 d theta 2 into d theta 1 by 2 plus 2 sigma r1 d theta 1 and d theta 2 upon 2 is equal to Pi minus P naught R1 R2 d theta 1 into d theta 2. Now this 2 gets cancels out. So we get sigma R2 d theta 2 d theta 1 plus sigma R1 d theta 1 d theta 2, which is equal to Pi minus P naught R1 R2 d theta 1 into d theta 2. Now in all these terms we have d theta 1, d theta 2 as common, so we can cancel it out. So finally we get sigma R2 plus sigma R1 will be equal to Pi minus P naught into R1 R2. Now on rearranging, we can now write down the final equation. If we divide the terms by R1, R2, what we will get? We will get sigma upon R1 plus sigma upon R2 will be equal to Pi minus P naught. This is the Young's Laplace equation which I was talking about. So the difference in pressure Pi minus P naught can be expressed as sigma upon R1 plus sigma upon R2, and where sigma is the surface tension of the liquid which is in contact with any specified liquid, be it a gas or any other immiscible liquid. Now, if the liquid surface coexists with any another immiscible liquid or suppose a gas also on both the sides, then the surface tension force appears on both the concave side and the convex side, and the net surface tension force on the surface will be twice of what we have got. So, if there are on both the sides, if there are liquids, so we will have a net pressure of del P, which will be equal to twice of sigma upon R1 plus sigma upon R2. Now, for this, let us try to see what happens in case of a liquid droplet or in case of a liquid bubble. Now, see, in case of a spherical bubble, the radius of curvature will be same. So, for spherical bubbles, we have R1 is equal to R2. Let us say that it is equal to R. So for that we have del P will be equal to twice of sigma upon R plus sigma upon R, which is equal to 4 sigma upon R. Or in terms of diameter, if you want to write, it will be equal to 8 sigma upon D. If we take the case of a liquid droplet, for droplets, again we have the radius as R1 is equal to R2 is equal to R. Here in this case, both the terms will be there because on one side there will be liquid and on the other side there will be another liquid, or you can say gas, because spherical bubble, in case of spherical bubbles we have two interfaces, since we have air both inside and outside, and this is the liquid for which we have got the bubble. So for both the interfaces, we will take sigma upon R, and we will say that there will be 4 sigma upon R or 8 sigma upon D of pressure difference. In case of a spherical liquid droplet, again R1 will be equal to R2, which will be equal to R, but what we will take here, del P will be equal to then P will not be equal to twice, but simply sigma upon R plus sigma upon R. So this becomes 2 sigma upon R, which is equal to 4 sigma upon D. Now, see this expression for pressure difference for spherical bubble and droplets can be calculated in a very simple way. Let me explain you that simple way. Suppose, let us say that this is a liquid droplet which is filled with the liquid. This is a droplet of liquid. Now, if we divide it into two parts, we will get a figure like this. Now, this is filled with liquid. So, we have one interface that is formed here. Let us say that the coefficient of surface tension for the given liquid, it is sigma. So, there will be sigma force due to surface tension that will be acting along the interface like this. Let us say that the radius is R, the radius of the given droplet is R. Now, from the surface tension consequence, we have a net pressure difference of del P that is acting in this direction. Now, the force due to surface tension, this will be calculated as sigma into the characteristic length of the interface, which is the circumference. Now the circumference, since the radius is r, we have sigma into 2 pi r. Force due to pressure that will be acting Fp will be equal to del P into the area upon which the pressure is acting, and the area for this will be equal to pi r square. So we have del P into pi r square. So in equilibrium, if we do a force balance, we get Fst must be equal to force due to pressure. So sigma into 2 pi r will be equal to del P into pi r square. So finally, for pressure difference del P, we have sigma into 2 pi r upon pi r square. Pi gets cancelled, r gets cancelled, and so we have got 2 sigma upon r or 4 sigma upon d. So in case of a liquid droplet, the pressure difference is equal to 2 sigma upon r. Now what happens if we take the case of a bubble? See, in case of a liquid, we have just one interface which is formed, but in case of a bubble, we have two interfaces. Let me again draw the half of the bubble. So we have two interfaces that are existing in case of a liquid bubble, because inside we have air, outside also we have air, and this is the liquid for which the bubble is. So for this case, we will have the surface tension force that will be acting on the outer interface, as well as the surface tension force will also be acting on the inner interface. For the outer interface, we have force due to surface tension. It will be equal to sigma into 2 pi r. And for the inner interface, again we will take sigma into 2 pi r, as the liquid film is you can say the width of the liquid film is negligible and the radius is considered the same. So overall we have the force due to surface tension will be equal to 2 sigma into 2 pi r. And here also there will be a force due to pressure that will be acting. If the intensity of pressure is del P, so force due to pressure it will be equal to del P into pi r square. So again, in equilibrium, force, if we do a force balance, what we get here? We get del P into pi r square will be equal to 2 sigma into 2 pi r, or del P will be equal to 2 sigma into 2 pi r upon pi r square. So pi gets cancelled, 1 r gets cancelled. So here we have 4 sigma upon r, which is equal to 8 sigma upon d. So this is for bubble. So in case of a liquid droplet, we have a pressure difference of 4 sigma upon d, and in case of a bubble, we have 8 sigma upon d or 4 sigma upon r. We can apply the same for a cylindrical liquid jet and try to find out what will be the pressure difference. Let us calculate that also. Suppose we consider part of a liquid cylindrical jet. Suppose this is the cylindrical jet which we are taking. Let us say that the length of this cylindrical jet is L. So again here we will divide it into two parts. Now here the interface that is formed is along the curved surface area. So we will denote it on both the sides. So here also there is sigma that is acting. Here also there is sigma that is acting. So the net force due to the surface tension on this side will be sigma into L, and for this side we will take sigma into L. So force due to surface tension will be sigma into L plus sigma into L, which is 2 sigma L, and pressure, intensity of pressure is del P, and force due to pressure will be equal to del P into the area. What will be the area of this? This will be, since the length is L and the other side is 2R. So del P into L into 2R. Again, equating both, we get del P 2 del P L into R is equal to 2 sigma L. L gets cancelled and 2 also get cancelled out. So we have del P is equal to sigma upon R, or 2 sigma upon D. This is the case for a cylindrical jet. So finally, we can write the results of both the three cases. In case of a droplet, in case of a liquid droplet, what we have got? We have got 2 sigma upon R. For droplet, we have del P is equal to 2 sigma upon R. In case of a bubble, we got del P is equal to 4 sigma upon R. And for a cylindrical jet, we have del P is equal to sigma upon R. Now these final, the results are very important for numerical, so you must remember all these.